All right, guys, so what we're going to be talking about here is a smaller topic that we just need to discuss because it does show up on the AP test from time to time. There's probably not going to be an assignment or anything with this one, so don't freak out if you don't understand it. If you do, it's pretty easy to understand, I think, once you kind of look at it. But just be aware, this is a test that you can use in a very specific situation, and that's why it's kind of something that we don't look at very much, because the situation where we use this test in order to determine whether or not something is convergent, it has to meet a lot of criteria in order to do that. So let's just jump right in and look at it. Now, we talked about previously, when we were talking about infinite series, we talked about this special series, if you remember, called the harmonic series. Now, when we look at the harmonic series, we saw that basically what we said before was we said, okay, I'm looking at this, and when I go 1 plus 1/2 plus 1/3 plus 1/4, one way that we could look at it was that you can always, and this is, I don't know how much we really went into it, but one way you can look at it is you can always find enough numbers to group together. Like these three numbers grouped together, they add up to more than 1, so that's bigger than 1. And then the next 6 terms add up to be more than 1. And then the next 12 terms after that add up to be more than 1. And so what happens is you have 1 plus 1 plus 1, and since that's going on forever, don't try to think about this too much because it's kind of hard to be like, because the series goes on forever, you can always find another group of numbers that when you add all of them up, they're still going to add up to 1. So 1 plus 1 plus 1 plus 1 plus 1 over and over and over is an infinite sum. And it sounds kind of weird that it's going to take longer and longer, but because this series goes on forever, there are an infinite amount of 1s. There aren't as many 1s as there are terms, so don't think about that too much to be like, what? But there are an infinite amount of 1s. There's just more infinite amounts of terms. Anyway, don't worry about that too much. Okay? So that's how we were kind of able to show it a little bit using just kind of logic as far as what's going on. In reality, there's an easier way to prove it that doesn't hurt your brain quite as much, and it's what's called the integral test. And here's what the integral test says, and I know this looks a little bit confusing at first. It basically says if f of x is equal to a sub k for every k, and f is continuous, decreasing, and f of x is greater than 0 for x is greater than 1, then the integral from 1 to infinity of f of x and the integral from k, or not integral, excuse me, the sum from k equals 1 to infinity, either both converge or diverge. Now that is a ton of stuff, a lot of math terms saying, well, there's a lot going on here. So let me kind of explain a little bit what's going on. First of all, what it's saying is if you have a series that has a bunch of positive numbers that are always decreasing as they go further and further out, and that is key to being able to use this test. It's one of the reasons why we don't use it very often, because not all series do that. But as long as the series, as it moves out, each term from one to the next is always decreasing, and it's always positive, then what we can do is we can compare this series to an improper integral that behaves pretty much the same way as this series. Now again, that to me, when you hear that, you're like, what are you talking about? That doesn't make an awful lot of sense. So what we have to do is, if you remember, we looked at the improper integral, so we're going back to integrals just for a minute here, the improper integral from 1 to infinity of 1 over x dx, okay? When we did that, basically said, okay, when I take, and there's lots of different ways to prove that this was divergent, but one way we could prove that it was that integral was divergent was we took the antiderivative and then we plugged in the top and we plugged in the bottom. So I got the ln of absolute value of x minus the ln of 1, the ln of 1 of 0, the ln of infinity. That's not it. I meant to say infinity. Is infinity. That is not a specific number, which meant the area that existed between this curve and the x-axis was infinite. Now, if I was looking at a summation from, we'll just use n instead of k. So I've got n equals 1 to infinity of 1 over n. One way we could think about this, because again, this series is 1 plus 1/2 plus 1/3, on and on and on. If I wanted to do a Riemann sum, and it wouldn't matter which side you did it from, but let's say we wanted to do a left Riemann sum on this particular series, where the base of all of my rectangles is 1. And that's important if we did that the base is 1. Otherwise, this doesn't work very well. So if I did a Riemann sum where all the bases were 1, I would go 1 would be my base, and then to determine my height, I would just go straight up to the function at x equals 1. Well, the area of this rectangle is 1, and you can see that above the rectangle. Then the next area, the base would be 1, and the height would be 1/2. So I'd get 1 plus 1/2 plus 1/3, on and on and on, and that would go on forever. Well, that Riemann sum and that particular series that we're looking at, this Riemann sum, because we're using a left Riemann sum, is an over approximation. In other words, the area that I would use to, because this function is decreasing and we're using a left Riemann sum, we have an over approximation. Well, if this area is infinity, and I'm having an over approximation using my left Riemann sum, then that's going to be even more of an over approximation than infinity. So it's going to be infinity plus a little bit more. Well, if that's the case, and this right here is equal to infinity, this right or left Riemann sum is exactly the same as the summation right here. Okay? And so what we can say is, due to the fact that that is an over approximation, and I already know the exact area is infinity, then the summation must be infinity as well. Okay? If I was to look at 1 over n squared, again, I know that this function does this, and it's very, very important. And the nice thing on the AP exam when you see the integral test is you'll always see the function is continuous, positive, and decreasing. Because all of those things need to be true in order for us to use the integral test. I know from, if I do the integral from 1 to infinity of 1 over n squared, I can actually, or x squared, excuse me, I can find out what that is. When I take the antiderivative, I get negative 1 over x from 1 to infinity. When I plug that in, I get negative 1 divided by infinity minus negative 1 divided by 1. This is 0 minus negative 1 gives me positive 1. So I would know that this area from 1 to infinity is 1. What the integral test says is if that's the case, if I were to do a left Riemann sum, which is exactly the same as this summation, now this is key, you would not know what it adds up to. And that's important. I have no idea. Even though I know this area is 1 overall, because I would be doing a left Riemann sum to estimate what this summation is going to be, because you'd have 1 plus 1/4 plus 1/9, on and on and on, because I don't know what that's going to be. I don't know exactly what that's going to add up to. I can't say that it's going to be 1. What I can say, however, is I know it is not going to be infinity. Like, it is going to be an over approximation, so it's going to be a number bigger than 1, but it's not going to be enough bigger than 1 that you can say, oh, well, I know exactly what that is going to be. Okay? And so, and now hopefully that makes sense. I mean, the first term is 1, and then we're going to get bigger than that from there on out. Anyway, long story short, if you see the phrase continuous, decreasing, and positive, what you're asked to do on the AP test is take this infinite series and compare it to an improper integral where instead of using n, we are using x. If this series is divergent, then that means that, or excuse me, if that improper integral is divergent, that means the series is divergent. If that improper integral is convergent, then that automatically means that the series is convergent as well. The problem with this one is it is so specific to a very small amount of functions that it's not super helpful for us to use in general. And as we keep moving forward, you'll find out that there are other tests that are much more useful and way easier to tell whether or not a much more complicated series is convergent. We'll get to those eventually.